Hello there and welcome to the Sleepy Scientist. I'm so glad you're here. Whether you're tucked under a cozy blanket, listening while the kettle hums gently in the background, or simply letting your mind float like a balloon in the breeze, this video is your invitation to relax, unwind, and drift gently into that dreamy space where curiosity and calm meet. Tonight, we're entering the strange and beautiful world of quantum physics, a place where particles play hide-and-seek, cats become philosophical thought experiments, and the universe occasionally winks at you when you're not looking. It's a landscape so peculiar it might just make your pillow feel more grounded in reality. Now, a small word of caution. I do hope this video isn't too interesting. That's always the risk with quantum mechanics. If it keeps you awake, I can only apologize and offer the consolation that you may at the very least pick up a few delightful facts to impress a sleepy friend or a confused pet. But hopefully, with my calm narration and a gentle pace, your eyelids will get heavier before the electrons start behaving themselves. Before we dive in, I'd love to know where in the world are you listening from? And what time is it right now in your cozy corner of the cosmos? Pop it in the comments below. I always enjoy reading where and when these videos are keeping people company. And if you find yourself enjoying this quiet journey into quantum stranges, please do consider giving the video a gentle like and tapping that subscribe button. It helps this sleepy little corner of the internet reach more curious minds, and it means the world to me. One more thing before we begin. This video is for relaxation, curiosity, and bedtime wonder. It is not medical advice nor a substitute for professional care. Please always speak to a qualified health provider for any concerns about your sleep or well-being. All right, get comfortable, let your breath slow down, and when you're ready, we'll begin our quiet exploration into the invisible, improbable world of quantum physics. Let's take a gentle step into the world of quantum physics. Don't worry. You don't need a lab coat, a degree in mathematics, or even a firm grasp on reality. All you need is a bit of curiosity, a relaxed mind, and perhaps a warm beverage to keep your hands occupied while we wander through the quantum fog together. Now, quantum physics is a subject that has long fascinated and bewildered scientists, philosophers, and insomniacs alike. It's the branch of physics that deals with the very smallest things in the universe, particles so tiny that they make atoms look like beach balls. We're talking about electrons, photons, quarks, particles that don't behave anything like the solid, sensible objects we're used to in our daily lives. These particles play by a different set of rules, and those rules are, well, a bit peculiar. Classical physics, the kind you might have learned in school, deals with the world we can see and touch. You throw a ball and it arcs through the air in a nice predictable parabola. You drop a book and it falls to the floor. Gravity, momentum, force, everything neat and orderly. But the moment you shrink things down to the scale of the tiniest particles, that predictability starts to break down. The ball might not land where you expect. In fact, it might not land at all. It might just sort of exist in a probability cloud of possible locations until someone looks at it. Then, and only then, it makes up its mind. Sort of. This idea that particles behave unpredictably until observed is just one of many strange things we encounter in the quantum realm. And it's what makes this field so fascinating. You see, quantum physics is not just a branch of science. It's a collection of very peculiar questions that reality seems to ask us when we zoom in far enough. Let's begin with a simple thought. Imagine you're in a room with the lights off and someone tells you there's a tennis ball in the corner. You can't see it, but you're pretty sure it's there. If you switch on the light, there it is, right where you expected. In classical physics, that's how things behave. They're always somewhere, even if you're not looking. Now imagine that instead of a tennis ball, you're dealing with an electron. And instead of being in the corner, it's possibly in one corner or the other, or maybe both, or maybe somewhere else entirely. And until you switch on the metaphorical light, until you actually measure its position, the electron exists in a superposition of possibilities. It doesn't have a single definite position. It has a spread of them. It's like trying to find your car keys and discovering that they are on the kitchen counter, the bathroom sink, and inside the fridge all at once. And only when you reach out to grab them do they pick a spot and commit. This is one of the key ideas of quantum physics. Particles exist in a state of probability until they're observed. It's not that we just don't know where they are. It's that they truly don't have a definite location until we look. And yes, it sounds bizarre. Even Einstein didn't like it. He once famously quipped, "God does not play dice with the universe." To which the quantum physicist Niels Bohr replied, in essence, "Stop telling God what to do." The math that supports this idea is surprisingly precise, even if the idea itself feels hazy. We use something called a wave function, a mathematical expression that describes the probabilities of where a particle might be and what it might be doing. It's like a weather forecast, but instead of predicting rain in your area, it predicts where an electron might decide to be when you take a peek. And unlike a weather forecast, quantum predictions are scarily accurate. The odds match reality with uncanny precision down to decimal points so fine, they'd make your calculator blush. Let's take a moment to appreciate just how weird this is. In our normal everyday world, we rely on certainty. The coffee cup is on the table. Your feet are on the ground. The spoon is definitely not in orbit. But in the quantum world, certainty is a luxury we don't get. Instead, everything is a maybe, a might be, a shimmering collection of potential outcomes. Now you might wonder, if this stuff is so uncertain, how can we build anything with it? How can the universe function? And yet it does. That's the amazing part. Even though quantum behavior is full of probabilities, the large-scale world around us emerges from it with stability and structure. Billions of quantum may somehow add up to one very real table that doesn't suddenly vanish while you're sipping your tea. It turns out that once enough particles get together, like an atoms, molecules, and the stuff we're made of, their collective behavior becomes so well averaged that all those wild probabilities start to cancel out. The result, solid objects, predictable physics, apples that fall from trees instead of teleporting into low Earth orbit. In other words, classical physics reemerges from quantum physics when the numbers get big enough. Still, that doesn't mean the quantum world isn't lurking underneath, quietly powering everything. Every chemical reaction in your body, every flicker of electricity in your brain, every beam of light that bounces off your wall is governed by quantum rules. It's like discovering that all your furniture is made out of invisible spinning coins, and yet somehow your chair still holds you up. And it's not just small things that depend on quantum physics. The sun, for instance, wouldn't shine without it. Deep in its core, nuclear fusion relies on quantum tunneling, a process that allows particles to squeeze through energy barriers they shouldn't be able to cross. Without this magical quantum loophole, the sun would be a cold, lifeless sphere, and we wouldn't be here to marvel at the laws that make it glow. Speaking of marvels, did you know that lasers, transistors, and even the device you're listening on right now are all made possible by quantum mechanics? That's right. This very video owes its existence to the strange behavior of subatomic particles. If that's not delightfully meta, I don't know what is. Now, it's important to mention that quantum physics isn't some sort of magical wish fulfillment engine. There are a lot of misconceptions floating around out there, like the idea that your thoughts can directly influence the physical world because of quantum mechanics. As relaxing as that might sound, the reality is a bit less poetic. Quantum effects are real, but they don't let us bend spoons with our minds or teleport to Paris for a croissant. They operate under strict rules. Unusual rules, yes, but rules all the same. That said, the rules are fascinating. They tell us that particles can be in more than one state at once, that they can become entangled and affect one another across vast distances. That observation changes outcomes. That nature at its most fundamental level is not a machine but a probability dance. So as we ease into this strange and subtle realm, let your imagination stretch a little. Picture electrons not as dots, but as little clouds of possibility, each one a tiny echo of the mystery that underlies our universe. Quantum physics doesn't just challenge our understanding, it invites us to rethink what understanding even means. And as you lie there, perhaps half listening, half dreaming, consider this. The very atoms in your body once obeyed these rules too. In fact, they still do. You, in a very real sense, are made of quantum stuff. So perhaps it's not so strange after all. Maybe it's the classical world that's the illusion, and the quantum world, with all its oddness and wonder, is the true foundation of everything. Let that thought settle in gently. Not too quickly, just like a sleepy electron deciding where to be. Imagine a particle, just a simple one, maybe a little electron minding its own business. Now imagine a wall with two narrow slits cut into it. Behind that wall, a screen where we can catch anything that passes through the slits. So far, so good. You might think, a classic game of throw the particle through the slot. But what happens next? What has been happening in physics labs for over a century will gently twist your perception of reality. This is the double-slit experiment, one of the most elegant and unsettling demonstrations in the history of science. It looks innocent enough, just a bit of physics theater involving particles, barriers and screens. But what it reveals is so strange, so quietly mind-bending that it continues to baffle and delight physicists to this day. So, let's walk through it gently. Imagine we're launching tiny particles, say electrons, toward the wall with the two slits. If we close one slit and open the other, we'll get a pattern on the screen behind that matches what you'd expect. A thin cluster of hits aligned with the open slit. If we close that slit and open the other one, we get a similar thin line just in a different spot. Now comes the interesting part. If we open both slits, now we expect that the electrons will go through one slit or the other. Right. So the screen should just show a combination of the two thin lines we saw before. Logical, yes, but no, that's not what happens. Instead of two lines, the electrons form a pattern of alternating dark and light bands, an interference pattern. This is what we'd expect if we were firing waves, not particles. The light and dark bands show constructive and destructive interference, places where waves add up and cancel out. Let's pause here, because this is where physics starts whispering secrets. Electrons are particles, tiny discrete chunks of matter. You'd think they just go through one slit or the other like little pebbles. But somehow when both slits are open, they interfere with themselves. As if each electron is spreading out like a wave, going through both slits at once, interfering with its own path, and only then landing on the screen in a specific spot. That's strange. But it gets even stranger. Let's slow the experiment down. Instead of launching many electrons at once, we send them one at a time. Just a single electron, wait a bit, then another. Each one hits the screen as a single dot. No interference yet, just scattered specks. But as more and more electrons arrive, a pattern starts to emerge. And once again, it's an interference pattern. Even though the electrons were launched one at a time, had no other electrons to interact with, they somehow still form a wave-like pattern on the screen. Each one seems to be interfering with itself as if, brace yourself, it goes through both slits at the same time. How is that even possible? Well, this is one of the strange rules of the quantum world. Particles like electrons don't behave like little billiard balls. They behave like waves of probability. When not observed, an electron doesn't have a definite position or path. Instead, it exists in a cloud of possible states, a superposition. And that superposition includes the possibility of going through both slits at once. It's only when we measure the electron, when we observe which slit it went through, that the illusion collapses. The wave function chooses a definite state. It goes through one slit, and the interference disappears. The electrons now hit the screen in two neat clusters, just as we'd expect from ordinary particles. Observation changes the outcome, yes, that's right. Just by looking, we disrupt the electron's ghostly indecision and force it to make a choice. This is not just philosophical musing. This has been tested repeatedly with ever more sensitive equipment. Scientists have even tried clever tricks using detectors that could, in theory, observe the path without disturbing the electron directly. Yet, every time we gather information about which slit the electron went through, the interference vanishes. The act of observation itself changes the behavior of the particle. It's not that the electron is shy and doesn't want to be seen, it's that the very act of measurement collapses the range of possibilities into a single outcome. Before you look, it's a wave. After you look, it's a particle. Now, let's gently unravel the wave-particle duality. This is one of the foundational concepts of quantum mechanics. Entities like electrons and photons are neither just particles nor just waves. They are both and neither. They exhibit properties of each depending on how we observe them. Imagine you're at a concert. The music is smooth and continuous like a wave. But now imagine you're only allowed to hear the music in tiny snippets, short individual notes, one at a time. That's a bit like how particles behave. Sometimes they act like smooth, wavy energy fields. Other times they hit like little quantized packets. Light does this too. Photons can create interference patterns when passed through slits just like electrons. But they also come in discrete chunks, each carrying a specific amount of energy, hence a particle and a wave. Now, a natural question arises. Is the electron really going through both slits at once? Or are we just misunderstanding what's going on? And here's where quantum mechanics just shrugs politely and says, we don't know. All we can do is calculate probabilities. What is likely to happen? Not what is happening when we're not looking. The standard interpretation of this phenomenon, the Copenhagen interpretation, named for the city where Niels Bohr did much of his work, suggests that quantum systems don't have definite properties until they're observed. Until we interact with the electron, asking where are you? It has no defined position or path. It's a probability cloud, a smear of May. The act of measurement collapses the wave function into a single reality. Some people find this unsettling. Others find it beautiful. Reality in this view is not fixed, but fluid. It's not until we look that it crystallizes into something definite. Until then, it's potential. But not everyone agrees. There are other interpretations of the double-slit experiment. One is the many worlds interpretation, which says the electron does go through both slits, but in different universes, each possible path spawns a new branch of reality. So in one world, the electron went through the left slit, and in another the right. The interference pattern arises because these universes are still entangled in some way. This idea has its own strange implications. If every quantum possibility creates a new universe, then there are countless versions of reality unfolding at every moment. Somewhere another version of you is watching the same video, but with a slightly different tea. Maybe lemon instead of chamomile. And then there's the pilot wave theory, which says particles do have definite paths, but are guided by a hidden wave that determines where they go. This wave creates the interference pattern, even though the particle only goes through one slit. It's like an invisible shepherd guiding a sheep along a complex quantum trail. But whichever interpretation you favor, the experiment itself remains undeniable. The double-slit experiment shows us over and over again that particles can behave like waves, that reality changes when we look, and that the world on the smallest scales is profoundly different from the one we experience every day. Let's try a gentle metaphor. Imagine you're dreaming, and in that dream you find a mysterious forest. You walk through the trees, but the path ahead constantly shifts. It's not fixed. It responds to your thoughts, your expectations, even your presence. When you look closely, the trees rearrange themselves. The path becomes solid only where you place your feet. Quantum physics is like that forest. It's a place of potential rather than certainty. Things don't just happen. They could happen in many ways, and it's only when we engage with them that they choose a form. The double-slit experiment is like a crack in the wall of reality, letting us peek into this shifting dream. A simple setup, slits, screen, particles, yet it opens a portal to the foundations of the universe. And perhaps most astonishing of all is this: we can repeat this experiment with electrons, with photons, with molecules, and even with large molecules like buckyballs, carbon structures made of dozens of atoms. As long as they're isolated enough from outside interference, they too form interference patterns. They too seem to behave like waves. That means wave-particle duality isn't limited to the tiniest building blocks of matter. It's part of a broader principle, a hint that maybe, just maybe, everything around us, everything we are, is secretly governed by the same ghostly rules. So, next time you flip a light switch, remember the photons pouring out of the bulb are making a quiet decision about how to behave, not because you're watching necessarily, but because the universe itself, it seems, only settles into shape when something within it pays attention. The double-slit experiment doesn't just teach us about electrons. It teaches us about reality, about the space between knowing and guessing, about the strange rippling line between what is and what could be. And as you drift into sleep, let that idea echo gently that underneath the surface of everything, the universe is a soft sea of probabilities. And we, curious little observers, are part of the process that gives it shape. Let us ease our way deeper into the quiet corridors of the quantum world. You've met particles behaving like waves, watched electrons stroll through two doors at once, and seen reality hesitate until it's observed. Now, it's time to meet one of quantum physics' most mind-bending ideas: superposition. It's a beautiful word, isn't it? It sounds almost poetic, like something you'd find in a dream or in the folds of a cloud. And in a way, it is. Superposition is the quantum version of keeping your options open. It's a particle saying, I could be this, or I could be that, or perhaps both at once. Let's not decide just yet. At the heart of superposition is this simple but profoundly strange notion. Until something is measured or observed, it can exist in multiple states at the same time. Imagine you're flipping a coin. In our everyday world, it's either heads or tails. Once it lands, the outcome is fixed. But in the quantum world, a particle is like a coin suspended midair, spinning endlessly. Not just flipping, but somehow being both heads and tails simultaneously. Only when you catch it, only when you observe it does it settle on one result. It's not that we're unsure what state it's in. It's that the particle literally exists in a superposition of states until we look. The possibilities aren't just unknown. They're real and present. This idea is not just theoretical. It's built into the mathematics of quantum mechanics and confirmed by countless experiments. Let's explore it gently. Let's say we're dealing with an electron again, our favorite misbehaving subatomic rascal. An electron has a property called spin. Spin is a bit like a tiny arrow pointing in a direction, though not a physical spinning in the usual sense. It's a quantum number, a kind of internal compass. If we measure the spin of an electron along a vertical axis, we'll find it's either spin up or spin down. Those are the only two options. But here's where it gets weird. Until we actually measure it, the electron is in a superposition of both spin up and spin down. It's not undecided. It's not 50-50. It's both at the same time. We represent this with a mathematical expression that combines both states. A weighted blend of spin up and spin down. These weights are complex numbers, and they describe the probabilities of what we'll find when we look. But the important part is this. The electron is not secretly one or the other, it's both. A superposition. The moment we measure it, the superposition collapses into one outcome. It becomes either spin up or spin down, and the probabilities we calculated tell us how likely each result is. But before the measurement, it lived in the land of and. Now, if this is starting to feel a little slippery, don't worry. You're in excellent company. This concept is famously illustrated by one of the most misunderstood thought experiments in all of science. Schrödinger's cat. Ah yes, the feline metaphor that launched 1,000 philosophical debates. In the 1930s, Austrian physicist Erwin Schrödinger proposed this thought experiment to highlight the oddness of quantum mechanics when applied to everyday objects. Here's how it goes in a calm and metaphorical tone. Imagine a cat in a sealed box. Inside the box is a radioactive atom with a 50% chance of decaying in a given period. If it decays, it triggers a mechanism that releases poison gas. If it doesn't decay, the cat is fine. Because the atom is a quantum system, it exists in a superposition of decayed and not decayed until it is observed. That means in quantum terms the cat is also in a superposition, both dead and alive, not one or the other, both simultaneously. Only when you open the box does the cat's fate become definite. Until then it exists in a fuzzy ghost-like blend of both life and death. Now, before we get too emotional about poor Schrödinger's imaginary cat, it's important to understand that he didn't invent this thought experiment to say the cat is actually both dead and alive. In fact, he was critiquing this idea. He wanted to show how absurd quantum principles seem when applied to large visible objects. Surely, he thought, we're missing something. And yet all these decades later, physicists still lean on this cat metaphor, not because they believe cats really live in limbo, but because it illustrates just how strange superposition is. In practice, the idea of superposition doesn't tend to last long for big objects like cats or chairs or sandwiches. That's because the moment a quantum system interacts with its environment, the superposition collapses. This process is called decoherence. It's like a whisper getting drowned out by the noise of the world. The delicate quantum state is broken by countless interactions. Air molecules bouncing off it, photons hitting it, gravity doing its thing. That's why we don't see superpositions in our everyday lives. Your morning toast never exists in both toasted and untoasted states, sadly. But on the quantum scale, on the scale of electrons, photons and atoms, superposition is very real, very strange, and very important. So important, in fact, that it powers one of the most exciting technologies of the 21st century, quantum computing. In a classical computer, information is stored in bits. Each bit can be a 0 or a 1. That's it, just one or the other, a digital on-off switch. But in a quantum computer, the fundamental unit of information is a qubit, and qubits can exist in a superposition of 0 and 1. That means they can be both at the same time. It's not just flipping a coin. It's keeping all possible outcomes in play at once. With many qubits entangled and superposed, a quantum computer can explore an enormous number of possible solutions simultaneously. This doesn't mean it's faster in the traditional sense, but it's extraordinarily powerful for certain types of problems like factoring large numbers, simulating molecules, or optimizing complex systems. It's as if you're trying to find your way out of a maze, and instead of choosing one path at a time, you walk all paths at once until you find the exit. That's the power of superposition. Not just a strange curiosity, but a new tool for exploring the possibilities of nature. Now, you might wonder if superposition is real, and if particles can exist in multiple states. Does that mean the universe itself is in a superposition? It's a tempting thought. After all, if one electron can be in multiple states and the universe is made of electrons and their friends, maybe reality itself is built from layers of May. Some physicists think so, others aren't so sure. And quantum mechanics, for all its precision, doesn't take a position either way. That's one of the great ironies of quantum physics. The math is crystal clear. The predictions are astoundingly accurate, but the meaning behind it all, that's still wide open. What we do know is this: superposition is not just a trick of the mind. It's not a metaphor or a philosophical pondering. It's a fundamental aspect of how particles behave when left undisturbed. It's been measured, tested, and verified in laboratories around the world. It's built into the way atoms bond, how light behaves, how stars shine, and how the very fabric of our universe evolves. And yet, despite all that, superposition remains one of the most softly surreal features of reality. It asks us to let go of certainty, to accept that something can be more than one thing at once. That existence is not a yes or no question, but a quiet, maybe waiting to be answered. So, as you lie back, letting your thoughts wander gently, consider this. Every time you look at the world, you're collapsing a cloud of possibility into a moment of reality. Every blink, every thought, every sigh is part of the great cosmic process of observation. And in the spaces between those moments, in the hush before the wave becomes a dot, there is a universe that hasn't quite decided what it wants to be. Maybe you haven't neither, and that's perfectly okay. Let us float now into one of the gentlest, yet most unsettling truths of the quantum world. The uncertainty principle. It's not loud or flashy. It doesn't involve mysterious cats or cosmic wave functions collapsing in a dramatic puff, but it quietly reshapes how we understand the very act of knowing something. In the quantum world, even knowledge itself has boundaries. This idea is most famously associated with Vera Heisenberg, a German physicist who in the late 1920s introduced a principle so fundamental that it bears his name to this day. The Heisenberg uncertainty principle. Let's begin softly. In our everyday life, we take it for granted that we can know where something is and how fast it's moving. If you're watching a car drive past your window, you can see it's 10 m away and moving at 30 km. Those two pieces of information, position and velocity, come together in your brain without effort. No one tells you that you can only know one at a time. That would be a very confusing commute. But in the quantum world, this kind of certainty breaks down. At the level of electrons and photons and their tiny companions, there's a fundamental limit to how precisely we can know both position and momentum at the same time. Let's unpack that. Position in this case means where a particle is. Momentum means how fast it's moving and in what direction. And the uncertainty principle tells us the more precisely we know one, the less precisely we can know the other. It's not a matter of instruments being clumsy or measurements being difficult. It's not about being in the dark, and needing a better flashlight. It's that nature itself does not allow us to pin down both quantities with absolute precision. The universe keeps some things permanently blurred. Imagine trying to take a picture of a firefly in a dark room. The moment you shine a flashlight on it to see exactly where it is, the light startles it and it moves. You might catch its position, but you've disturbed its momentum. Alternatively, if you track its motion over time to figure out how fast it's going, you might lose track of where it started. The more clearly you define one piece of the puzzle, the fuzzier the other becomes. This, at its heart, is what Heisenberg revealed. The world at the quantum level is not a neat and tidy place full of objects with fixed attributes. Instead, it's a symphony of uncertainty, an ever-shifting landscape of probabilities where knowing one truth gently erases another. Mathematically, the uncertainty principle is usually written like this: dx times dip greater than or equal to h bar divided by 2, where delta x is the uncertainty in position, delta p is the uncertainty in momentum, and h bar is a very tiny number called the reduced Planck constant. But don't worry, there's no need to memorize equations here. All you need to understand is that there is a minimum level of uncertainty baked into the universe. There's a limit to how well defined certain pairs of properties can be. And this isn't just true for position and momentum. There are other pairs of properties in quantum mechanics that obey similar uncertainty rules. For example, the more precisely we know the energy of a system, the less precisely we can know how long it will stay in that state. It's as if the universe allows you to borrow energy for a short time as long as you pay it back quickly. This is part of what allows virtual particles to pop in and out of existence. And it plays a role in the inner workings of everything from atoms to black holes. But let's stay focused on our original pair, position and momentum. Why is this uncertainty so fundamental? What causes it? The short answer is that particles are not little dots. They are quantum systems described by wave functions. And in the world of waves, sharpness in one domain always creates fuzziness in another. Think of a pure musical tone like a single clear note from a tuning fork. It lasts a long time and has a very specific frequency. But if you strike the fork quickly and let it die out right away, the note becomes less clear. You start to get a blend of frequencies. The more precise you are about when the note happens, the less precisely you can define what note it actually is. The same is true for particles. A perfectly well-defined momentum represented by a smooth infinite wave means that the position is completely spread out. You know how fast it's moving, but you have no idea where it is. On the other hand, if you confine a particle to a small space, like boxing it in, the wave function becomes sharply peaked in position, but it spreads out wildly in momentum. This isn't a quirk of the math. It's a statement about the nature of things. So what does this mean in practice? Does it matter? Oh yes, immensely. The uncertainty principle is one of the reasons why electrons don't fall into the nucleus of an atom. You might think that since opposite charges attract, an electron should spiral inward toward the positively charged nucleus, collapsing the atom like a dying star. But the uncertainty principle stops this from happening. If the electron were to collapse into a very tiny space, its position would be extremely well defined. That would force its momentum and therefore its energy to become wildly uncertain. It would require the electron to gain enormous kinetic energy, essentially pushing it back out. So the atom holds its shape stable and structured thanks to the delicate dance of uncertainty. Without this principle, chemistry would collapse. Atoms would not have size. Molecules would not form. Matter, as we know it, would not exist. It's one of those quiet facts that holds the world together while asking for very little attention. Now, let's take a peaceful moment to imagine what this uncertainty feels like. Picture a blurry photograph, not out of focus exactly, but soft, dreamlike. In the distance, you think you see something, a figure, a movement, a shape. But as you focus harder, the rest of the image seems to slip away. The more you pin down one detail, the more the rest fades into the mist. That's quantum uncertainty. It's not chaos. It's not randomness in the everyday sense. It's a profound and structured indeterminacy, an elegant reminder that we don't just observe the universe, we participate in shaping what can be known. Sometimes people ask whether this uncertainty reflects a limit of human knowledge or a limit of nature itself. And the answer, according to quantum mechanics, is that it's nature's limit. It's not that we haven't built a good enough microscope. It's that reality on the smallest scales is painted with a brush that refuses to make sharp lines. Now, you might be wondering if this uncertainty is noticeable in everyday life. The answer is not really. The numbers involved are so small that for objects larger than a molecule, the uncertainty becomes imperceptible. You could know the position and speed of a tennis ball to an absurd degree of precision without running afoul of Heisenberg's limits. But at the quantum scale, at the level of electrons, neutrons, photons, and tiny particles flitting around in the vacuum, there the uncertainty principle reigns supreme. It defines what can and cannot be known. It puts a soft edge around every fact. It draws a curtain between possibility and measurement. Some people find this idea unsettling, the loss of perfect knowledge. The idea that we live in a universe with boundaries on certainty can feel like a loss of control. But there's another way to see it. The uncertainty principle is also a gentle invitation to let go a little, to release the need for total precision, to understand that even at the most fundamental level, nature allows room for flexibility, for openness, for the beautifully indeterminate. It reminds us that the world is not rigid. It breathes, it shimmers, it dances between being and becoming. And perhaps in the quiet of the night, as your mind drifts between thoughts and dreams, that's the most comforting truth of all. That even reality at its deepest level has a softness to it, a blur, a breath, a margin of mystery. And that mystery is not a flaw, it's a feature. Let's take a deep breath and slowly tiptoe into one of the most enchanting and slightly eerie corners of the quantum world: entanglement. A word that in ordinary life might describe a set of tangled earphones or an awkward relationship, but in quantum physics refers to something far more mysterious, something that even made Albert Einstein squirm in his armchair. Quantum entanglement is the phenomenon where two or more particles become so deeply connected that the state of one instantly affects the state of the other, no matter how far apart they are. And I do mean no matter how far they could be on opposite ends of the galaxy, and yet still share a bond so perfect, so instantaneous, it appears to defy the limits of space and time. Einstein famously called it spooky action at a distance. And to be fair, he wasn't wrong. It is spooky, but it's also very real. Let's explore this gently with a clear mind and a comfortable cushion, because this is where quantum physics gets personal. To begin, imagine you have a pair of particles, let's say electrons. Now, electrons have a quantum property called spin, which, as we've touched on before, is a bit like a tiny arrow pointing up or down. But again, not a literal spinning, just a quantum quality that can be measured in specific directions. You prepare these two electrons in a very special way so that their total spin is balanced. If one ends up being measured as spin up, the other must be spin down. Think of it like cosmic choreography. Whatever one does, the other must do the opposite to keep the symmetry intact. Now, here's where the magic begins. You separate these two entangled particles. You send one to the far side of your lab and the other to a different continent. Maybe one's in Paris and the other's sipping tea in Tokyo. Then you measure the spin of the electron in Paris and find that it's spin up. Instantly you know the electron in Tokyo must be spin down. Not because you looked it up in advance, but because the act of measuring one determines the state of the other. It's not that the second particle had a hidden spin all along. According to the mathematics of quantum mechanics, the particles didn't have defined states until the moment of measurement. They existed in a shared superposition, a sort of combined wave function, and only when one is observed does the whole wave function collapse into a definite outcome for both particles. That's the heart of quantum entanglement. Measurement of one particle immediately affects the state of its entangled partner, regardless of the distance between them. This seems to go against one of the cornerstones of modern physics, that nothing, absolutely nothing, can travel faster than the speed of light. Information, particles, messages, they all have to obey that cosmic speed limit. So, how is this possible? Well, here's the comforting truth. Entanglement doesn't involve any information being transmitted in the classical sense. That's what saves it from violating the speed limit. When you measure one particle and see it spin, you learn something about its partner. Yes, but you couldn't use that to send a message. There's no way to control the outcome of the first measurement. So, you can't use entanglement for faster-than-light communication. No cheating the universe with instant texts. It's like opening two envelopes that were sealed together with a coin inside each. One heads, one tails. You open your envelope and see heads and instantly know your friend across the world has tails. It's surprising only if you thought the coins were random. But in quantum mechanics, the coins weren't fixed. They were undefined until the moment one was opened. And that's what makes it so puzzling. Now, let's pause to reflect. Entanglement isn't just a weird idea. It's a real experimentally verified phenomenon. In the early 20th century, Einstein, along with colleagues Boris Podolsky and Nathan Rosen, tried to poke holes in the theory. They proposed what's now called the EPR paradox, arguing that quantum mechanics must be incomplete. They thought that there must be hidden variables, unknown properties buried within each particle, deciding their fate ahead of time. But then came John Bell, an Irish physicist who in the 1960s devised a clever mathematical way to test whether hidden variables could be real. They can be correlated, but quantum mechanics predicts correlations that go beyond those limits. So Bell suggested experiments that could compare the predictions of quantum theory with the predictions of hidden variable theories. And when those experiments were carried out starting in the 1980s and repeated many times since, the results overwhelmingly supported quantum mechanics. The entangled particles behaved just as quantum theory predicted. The weird correlations really were stronger than any hidden variable model could account for. Entanglement is real. Nature is non-local. The universe, it seems, is more connected than our common sense might allow. Let's gently take this one step further. Entanglement isn't just for tiny particles. In carefully controlled experiments, researchers have entangled large molecules, atoms, even clumps of light. Scientists are even working toward entangling tiny mechanical resonators, objects that can be seen with the naked eye. The boundaries of quantum behavior are expanding slowly into the classical world, and in the world of quantum information, entanglement has become more than a curiosity. It's a resource, something to be harnessed, used, and explored. Let's drift into a few real-world applications softly and calmly. Quantum cryptography, for instance, uses entanglement to ensure secure communication. If two people share entangled particles, any attempt to eavesdrop on their communication disturbs the entanglement and is instantly detectable. It's like a magical lock that warns you if someone even thinks about picking it. Quantum teleportation is another beautiful and strange idea. It doesn't involve beaming someone through space like in science fiction, but it does allow the quantum state of one particle to be transferred to another using entanglement and a bit of classical communication. Here's how it works very gently. You have three particles A, B, and C. Particles B and C are entangled. Particle A has a quantum state you want to teleport. You perform a special kind of joint measurement on A and B, which destroys A's original state, but imprints information onto C across space with a classical message telling the result of the measurement. The person on the other end can recreate the original quantum state in particle C. No matter is moved, no energy is transmitted faster than light, but the quantum state has been transferred, teleported. And this is not theoretical. It's been done many times in laboratories, including over distances of hundreds of kilometers. Quantum teleportation is a real and active field of research, and it all hinges on entanglement. Entanglement also underpins the architecture of quantum computers. In these systems, qubits aren't just independent bits. They're entangled with one another, forming complex webs of quantum relationships. These connections allow a quantum computer to process enormous combinations of possibilities in parallel far beyond what classical computers can do for certain problems. But beyond the technology and theory, entanglement invites us to think differently about separation. In the classical world, if two things are far apart, they're independent. What happens to one doesn't affect the other. But in the quantum world, distance is not so decisive. Entangled particles act as a pair no matter how far they're pulled apart. It's as if the universe, at its deepest level, remembers that things were once together. Now entanglement is delicate. It can be easily disrupted by noise, heat, and random interactions. This is one reason why building a stable quantum computer is such a daunting task. Entanglement needs quiet. It needs stillness. It needs isolation, like a whisper carried between two souls in a crowded room. But in those rare, quiet conditions, entanglement shows us that reality isn't made of independent parts. It's made of relationships. In the quantum realm, to be is to be entangled. To exist is to be part of a whole. And that whole stretches across space and time in a way that defies our everyday intuition. As you settle into stillness, let that thought rest gently in your mind. That across this vast, expanding universe, there are particles that were born together, that danced in unison, and that even now, perhaps light years apart, still echo each other's movements. Entanglement reminds us that the world is not a collection of separate pieces, but a subtle interconnected tapestry, one where threads tug on one another across the stars. And in that quiet connection, maybe, just maybe, there's a hint of something deeper. Not just physics, not just mathematics, but a kind of harmony woven into the fabric of existence itself. Close your eyes for a moment, unless you're operating heavy machinery, and picture a quantum particle drifting gently through space. It's calm, weightless, unbothered by the classical rules we hold so dear. It exists in a superposition, a cloud of possibilities, occupying many states at once. It hasn't committed to a definite path or position. It is free, but then someone looks and everything changes. This chapter is about something called the observer effect, a cornerstone of quantum mechanics and a source of endless debate, confusion, and the occasional cup of strong tea. The observer effect is the idea that the act of measuring or observing a quantum system fundamentally alters it. It's not just that the measurement tells us what the system is doing. It's that the measurement changes what the system is doing. Observation doesn't just reveal reality, it helps define it. Now, in our everyday world, observation seems innocent. You can check the weather without changing it. You can peek at your phone without affecting the internet. You can admire a sunflower without altering its geometry. Unless, of course, you get too close. But in the quantum world, observation is never passive. It's more like participation, like touching a soap bubble. The very act of reaching out changes the thing you're trying to study. Let's explore this with a soft metaphor. Imagine you're walking through a dark forest with a lantern. You shine your light into the trees, and suddenly you see a deer. Now you know the deer is there, but your light has startled it, and now it moves. By observing it, you've changed its behavior. That's a bit like what happens in quantum measurement. At the quantum level, we often rely on delicate interactions to learn about particles. For instance, to find out where an electron is, we might bounce a photon of light off it. But that photon doesn't just gently reveal the electron's position. It also pushes it just a little. It changes the electron's momentum. So the more precisely we try to measure the position, the more we disturb the momentum and vice versa. This is one reason why the uncertainty principle exists. Measurement imposes limits, but there's more to it than just physical disturbance. Quantum theory tells us that a particle doesn't have definite properties like position or momentum until they're measured. Until then, these properties exist as a spread of probabilities, a wave function. An observation causes the wave function to collapse. In that moment, the particle chooses a definite state it commits. This collapse of the wave function is one of the great mysteries of quantum physics. It's as if the universe is a great story being written in pencil, and each measurement is an eraser wiping out all the other possible endings except one. Before we look, the electron might be here or there or anywhere in between. But when we measure it, all of that potential collapses into a single sharp result. This raises a fascinating question. What exactly counts as a measurement? Does it have to be done by a person, a scientist in a lab coat with a clipboard, a curious cat, or is any interaction with the environment enough? In the early days of quantum theory, some physicists wondered whether consciousness itself might be required to collapse the wave function. This idea, sometimes referred to as the consciousness causes collapse theory, suggests that it is the mind of an observer that finalizes quantum outcomes. That reality doesn't really exist until someone looks at it. This is an intriguing notion, one that tickles the edges of both philosophy and science fiction. But most physicists today lean away from this view. While it's a captivating idea, it introduces complications without offering testable predictions. Instead, many scientists believe that measurement doesn't require a conscious observer, only an interaction that irreversibly entangles the quantum system with its environment. This brings us to a gentler, more accepted idea: decoherence. Imagine a quantum system like an electron floating peacefully in isolation as long as it remains undisturbed. It maintains its strange quantum properties: superposition, entanglement, uncertainty. But the moment it interacts with its surroundings, say a stray photon, an air molecule, or even the measuring device itself, it becomes entangled with that environment. The quantum state spreads into the surroundings like ink bleeding into water. The clean, delicate wave function breaks down. The system decoheres. It no longer behaves like a quantum object, but like a classical one. The fuzziness disappears. A choice is made. So measurement in this view is just another kind of entanglement, one that pulls the quantum system out of its quiet possible states and locks it into a definite reality. But even with decoherence, there remains a deep mystery. Why do we see only one outcome? If a quantum system exists in a superposition, if it's both A and B, why do we always measure either A or B and never both? Why does the wave function collapse into a single state? Some physicists have tried to avoid this problem altogether by rejecting the idea of collapse. The many worlds interpretation, for example, says that all possible outcomes do occur, but in separate branching universes. When you measure the spin of an electron and it has a 50 chance of being up or down, the universe splits. In one branch, you see spin up. In another, your equally valid doppelganger sees spin down. In this view, the wave function never collapses. It simply evolves, and reality continually branches like a cosmic tree of possibilities. Now, whether you believe in many worlds, hidden variables, or spontaneous collapses, the observable truth remains. The act of measurement changes the system. Whether the universe splits, the wave function collapses, or decoherence blurs the lines, something changes when we look. But this isn't something to fear. It's something to wonder at, because it means that reality is not just sitting there waiting to be revealed. It's participating in a kind of conversation with us, a conversation where questions shape the answers, where curiosity carves out the structure of the world. Think about that for a moment. When you observe something in the quantum world, you're not just gathering information. You're changing the story. You're turning a page. You are making the universe commit to a sentence it hadn't written yet. This is not to say we're creating reality with our minds, but it does mean we're deeply woven into the fabric of it. Observers and participants, actors and audience. You might be wondering, but what about the moon? Does it not exist unless someone looks at it? Einstein once asked a similar question, perhaps with a bit of exasperation. And thankfully, the moon, being a big chunky object, interacting constantly with its environment, decoheres so thoroughly that it behaves classically at all times. Its wave function collapses so often and so completely that its quantum nature is drowned in noise. So yes, the moon is still there even when no one's looking. You can sleep peacefully. But for tiny particles quietly suspended in their quantum dreams, the story is different. They don't make up their minds until we ask. And sometimes the question is just as important as the answer. So as you lie there half in dream and half in thought, imagine this. Every photon, every electron, every dancing atom is living in a realm of possibility, a silent bollet of May. And when you look, when anyone looks, you pluck one thread from the tangle and make it real. You're not just drifting through the universe. You're brushing up against it, nudging it, listening for its next word, and whispering one back in the quiet of night. That might be the most comforting truth of all, that you matter. Not because the universe revolves around you, but because you are part of the way it unfolds. A quiet observer, a gentle participant, a co-author of the story written in particles and waves. Picture the universe as a vast ocean, not made of water, but of invisible energy fields stretching in every direction through every corner of space, even the ones we might think of as empty. In this ocean, ripples form. These ripples aren't caused by wind or stones, but by little excitations of the fields themselves. And those tiny ripples, they are the particles. The electron, the photon, the quark. Every fundamental particle is just a tiny disturbance in a deep, mysterious field that permeates all of reality, Welcome to the quiet and endlessly fascinating world of quantum field theory, the next step in our gentle exploration of quantum physics. So far, we've been thinking of particles like electrons and photons as point-like things, little dots like tiny specks of dust. And that's not wrong exactly. In many situations, it's useful to think that way. But to truly understand what particles are and how they behave across space and time, we need a slightly different lens. In quantum field theory, fields come first. The particles are simply what happen when you poke or stir those fields. Let's take it slow. Imagine a calm lake. The surface is smooth, undisturbed. This is like a quantum field in its ground state or its lowest energy. Now, toss a pebble into the lake. Ripples form, concentric circles moving outward. Those ripples are like particles. They're not separate from the lake. They are the lake just in motion. The pebble hasn't created a new object, it's just excited the field. This is how the universe works at its most fundamental level. There's an electron field, a photon field, a quark field, and many more. Each one fills the universe entirely. When we see a single electron, what we're seeing is a small localized ripple, a quantum of excitation in the electron field. That ripple moves, interacts, carries energy, and eventually vanishes, returning the field to its calm state. This might sound abstract, but it helps solve some deep problems in physics. For one, it gets rid of the idea that particles are separate, traveling objects moving through a vacuum. Instead, it's all fields all the time. Particles are just the punctuation marks, the little flickers of activity in this grand invisible sea. Now, you may be wondering, what about empty space? Isn't most of the universe just nothing? Not quite. According to quantum field theory, there is no such thing as truly empty space. Even what we call the vacuum is bubbling with activity. The fields are always there, always gently vibrating, even in the quietest corners of space. This leads us to another fascinating idea: vacuum fluctuations. These are tiny spontaneous blips in the fields. Brief random changes in energy that pop into and out of existence. It's as if the field twitches a little, momentarily, creating pairs of particles and antiparticles that quickly annihilate each other and vanish. These flickers don't last long. They exist for such brief moments, far too short to be detected directly in most cases. But their effects are real. For instance, they contribute to the Casimir effect, a very small force observed between two closely placed metal plates in a vacuum. The vacuum isn't empty. It's gently seething with virtual particles, which brings us to the next strange and beautiful concept: virtual particles. Now, the word virtual might make them sound imaginary, like something from a video game. But in physics, virtual simply means these particles can't be directly observed. They exist only in the calculations and influence interactions in subtle ways. For example, when two electrons repel each other, how do they know the other is there? They're not touching. There's no string connecting them. What carries the message? According to quantum field theory, they exchange virtual photons, not real observable particles, but mathematical intermediaries that transmit forces between the electrons. These virtual photons don't obey the usual rules that real particles do. They live in the quiet background of the fields, whispering force into existence. This is how all the fundamental forces work. The electromagnetic force is mediated by virtual photons. The strong nuclear force is carried by virtual gluons. The weak force responsible for radioactive decay involves virtual W and Z bosons. And even gravity, though not yet fully understood in the quantum realm, is thought to involve hypothetical virtual particles called gravitons. So here we are floating in a sea of fields. Particles rise and fall like gentle ripples. Forces are exchanged through silent ephemeral messengers. And beneath it all, the vacuum hums with quiet, jittery energy. But this picture also leads to one of the most puzzling questions in all of physics. Why doesn't the vacuum energy make everything explode? According to quantum field theory, all those vacuum fluctuations should contribute energy to space itself. And when physicists try to calculate how much energy is there, the number they get is, well, enormous. Staggeringly enormous. So enormous that if it were true, the universe would have expanded so rapidly after the Big Bang that stars and galaxies could never have formed. It would have been a brief hot blink, then darkness forever. But clearly that didn't happen. Our universe is here. We're here. The real expansion rate of the universe, The value associated with something called the cosmological constant is incredibly small compared to those predictions, off by a factor of about 1 followed by 120. That's not just a rounding error. That's the largest discrepancy between theory and observation in all of science. This is known as the vacuum catastrophe. And despite decades of work, physicists still don't have a satisfying answer. It's one of the great unsolved problems in modern physics. But let's not panic. Not here. In this calm space where wonder outweighs worry. Instead, let's marvel at the fact that the vacuum, the nothing, isn't really nothing at all. It's the stage on which everything plays out. A vast invisible canvas filled with potential energy possibility. Even light itself, that most familiar of quantum messengers, is born of these fields. A photon is just an excitation of the electromagnetic field. When you flip on a lamp, you're tickling that field, sending tiny ripples dancing across space to your eyes. And electrons too. Those little building blocks of atoms are not separate blobs drifting in space. They are disturbances in the electron field. Every electron in the universe is exactly the same because they are all made of the same underlying field. They're not individual snowflakes. They're notes played on the same cosmic instrument. This idea brings a strange kind of unity to the universe. Everything is made of fields. Particles are just patterns. When you see a spark or a rainbow or the glow of a candle, you're seeing fields in motion. The universe isn't made of objects. It's made of relationships, vibrations, echoes in invisible frameworks that underlie all of reality. Even you in your soft bed or cozy chair are made of fields, your atoms, your neurons, your thoughts. All of it arises from this quantum field playground. You're not separate from the universe. You are the universe briefly arranged in the shape of a person. Isn't that a lovely thought to drift off with? So next time you hear the word nothing, remember that the vacuum isn't truly empty. It's buzzing with unseen energy. It's alive with virtual particles flitting in and out of being. It's a cradle of creation humming quietly beneath the stars. And the particles we thought of as the fundamental building blocks, they are really the surface ripples of something deeper, something continuous and serene, something that doesn't just exist, it dances. In the end, quantum field theory invites us to let go of the idea that things are separate and solid. It asks us to imagine a universe where the smallest parts are not objects, but notes in a vast, unbroken symphony. And if that symphony happens to lull you gently to sleep, well, that may be the most quantum result of all. Imagine walking up to a solid wall. It's tall, thick, and made of stone. You press your hand against it, feel its cool surface push back, and know without a doubt you're not getting through. Not unless you have a wrecking ball, a magic key, or a very, very long weekend. Now imagine being a tiny quantum particle approaching a similar wall, a barrier of energy, not stone. According to the rules of classical physics, that particle should bounce back. No way through, no exceptions. But quantum physics smiles mysteriously and says, actually, there is a way. Welcome to the strange and wondrous world of quantum tunneling, a phenomenon that allows particles to pass through barriers they have absolutely no business crossing. It's not a trick. It's not cheating. It's just how the universe works deep down at its most fundamental level. Let's begin gently. In classical physics, an object needs enough energy to overcome a barrier. Imagine a ball rolling toward a hill. If it has enough speed, it can roll over the top and down the other side. If it doesn't, it stops and rolls back. Simple. Quantum particles, however, don't always play by these classical rules. In the quantum world, particles aren't just little dots flying through space. They're also waves, wave functions, spreads of probability. When a particle like an electron approaches a barrier, its wave function doesn't stop abruptly at the wall. Instead, it stretches into the barrier, even if the particle doesn't have enough energy to climb over it. And here's the strange part. The wave function doesn't stop on the other side of the barrier either. It keeps going, though weaker. This means there's a small but very real chance that the particle can be found on the other side, having seemingly passed through the barrier without ever having gone over it. That's quantum tunneling. It's as if the ball from earlier didn't have enough energy to roll over the hill, but sometimes just poof ends up on the other side anyway without breaking the hill, without climbing it, without leaving a trace. Just appears there, not because it cheated physics, but because physics at the quantum level is far stranger and far more generous with possibilities than we're used to. Now, let's clarify. The particle isn't teleporting through the wall, is not disappearing on one side and reappearing on the other. Instead, its wave function, the mathematical representation of its probability of being in a given location, extends into the forbidden region. If the barrier is thin enough and the particle's energy is close enough to the barrier's height, there's a measurable chance it can tunnel through. So, does this actually happen, or is it just a theoretical curiosity? It happens all the time. Quantum tunneling isn't just a strange idea tucked away in physics textbooks. It's responsible for real observable phenomena, some of which are essential to the universe as we know it. Let's start with something pretty important: the sun. You've probably heard that the sun shines because of nuclear fusion. Deep in its core, under immense pressure and heat, hydrogen atoms collide and fuse to form helium, releasing energy. That fusion process is the sun's power source. But here's the catch. Even with the intense conditions in the sun's core, classical physics says the hydrogen nuclei shouldn't get close enough to fuse. Their positive electric charges repel each other. It's like trying to push the same ends of two magnets together. They push back, so how do they ever touch? They don't. They tunnel. Quantum tunneling allows hydrogen nuclei to get close enough occasionally to overcome their repulsion and fuse. Without tunneling, the sun would not shine. And neither would any other star. Our very existence depends on particles quietly slipping through energy walls in the darkness. And it's not just stars. Quantum tunneling is also the principle behind semiconductors, which power all of our modern electronics. Your phone, your computer, your TV remote. They all rely on components like transistors and diodes, which are built on materials whose electrical properties are carefully controlled by quantum effects, including tunneling. There's even a kind of chip called a tunnel diode, which works because electrons tunnel through a thin barrier. It's designed to let them do so. And have you ever heard of scanning tunneling microscopes? These are powerful instruments that can image individual atoms. They work by bringing an extremely sharp metal tip very close to a surface, so close that electrons can tunnel between the tip and the surface. By measuring the tunneling current, scientists can create images with astonishing detail, all thanks to quantum tunneling. It's not just theory, it's technology. But perhaps one of the most magical aspects of tunneling is how it reminds us that probability is baked into the fabric of reality. Classical physics says, nope, not enough energy. Try again later. Quantum physics says, let's calculate the odds and give it a shot. The probability of tunneling depends on several things. How wide the barrier is how high it is, and the energy of the particle. A very high, thick barrier is unlikely to be tunneled through. A thin, low barrier much more likely. But in every case, the answer isn't yes or no. It's a probability. Reality at its smaller scales is not digital. It's not on or off. It's a shimmering field of chances. Let's pause and think about what this means philosophically. It means that impossibility in the quantum world is more flexible than we thought. That things we assume can't happen, particles crossing barriers they shouldn't be able to, can happen. Not always, not predictably, but often enough to matter. Quantum tunneling challenges the idea of hard limits. It invites us to see barriers not as walls, but as filters, things that reduce possibilities, but don't eliminate them entirely. There's always a chance, a slim, whisper-thin thread of possibility. And isn't that a comforting thought? Now, before we float off into abstraction, let's ground ourselves again with one more example. Radioactive decay. In certain unstable atomic nuclei, particles like alpha particles, which are essentially helium nuclei, are trapped inside a potential well created by the nuclear force. They don't have enough energy to escape the nucleus in the classical sense. They should stay trapped forever. But they don't. Sometimes the alpha particle tunnels out. It slips through the nuclear potential barrier and escapes, resulting in radioactive decay. This is why some elements are unstable. Their particles are tunneling out of the atomic nucleus step by step, second by second across millions of atoms. A slow, quiet leakage of mass and energy written in quantum ink. This is not just a curiosity. It's how we date ancient fossils, power spacecraft, and understand the structure of matter. So, to recap gently, Quantum tunneling is the process by which particles move through energy barriers they shouldn't be able to cross based on the strange probabilistic nature of their wave functions. It's responsible for the light of the stars, the function of our electronics, the slow decay of radioactive elements, and the images we take of atoms themselves. It's everywhere, and yet it's completely invisible in our day-to-day life. You don't tunnel through walls. Your toast doesn't disappear from the plate and reappear in the hallway. That's because the probabilities involved for large objects like us are so small, they might as well be zero. For a tennis ball to tunnel through a wall, you'd need to wait longer than the lifetime of the universe, even longer than the lifetime of many universes. But at the scale of electrons, protons and neutrons, at the scale of atoms and molecules, tunneling is not only possible, it's commonplace. The quantum world is full of quiet miracles. So the next time you see a spark of electricity or a beam of light, or even the shimmer of starlight on a calm night, think of the countless particles tunneling their way through barriers. Tiny acts of rebellion against impossibility. Gentle, persistent, successful. They don't force their way through. They don't climb the hill. They find another way, a quantum way. And maybe that's a lesson we can carry even outside of physics. That some obstacles aren't overcome with power, but with quiet persistence, with probability point, with patience. That even when things seem impossible, the universe sometimes leaves the door slightly open, just enough for something small and extraordinary to slip through. Let's take a moment now to imagine a world where the word maybe is not a sign of indecision, but a source of power. A world where things don't have to be one or the other. They can be both simultaneously, and where information isn't stored as a binary yes or no, but as an elegant swirling superposition of possibilities. Welcome to the world of quantum computing. Now, before you start picturing tiny laptops hovering in a cloud of probability, let's gently unpack what this actually means. Quantum computing is not science fiction. It's not time travel or magic or wishful thinking. It's a very real and rapidly developing field that uses the strange rules of quantum physics to process information in ways that ordinary computers simply cannot. But to understand why quantum computers are so special, we first need to look at how classical computers work, the ones we use every day. At the heart of every classical computer are bits. Bits are the basic units of information. Each bit can have a value of either 0 or 1. That's it. It's very tidy, very binary, very yes or no. Everything your computer does, whether it's sending an email, editing a video, or running this very voiceover, is done using long strings of zeros and ones processed by circuits that turn on and off in very specific ways. It's remarkable, really. Modern classical computers are powerful, elegant machines, but they do have limitations. There are certain types of problems, especially ones that involve enormous numbers of combinations, that classical computers struggle with. Problems that would take trillions of years to solve, even with the fastest processors available today. That's where quantum computing comes in. Instead of using bits, quantum computers use QS, short for quantum bits. And qubits are well weird. A classical bit, as we said, can be 0 or 1. But a qubit can be both 0 and 1 at the same time, thanks to a quantum phenomenon called superposition, which we explored earlier. Imagine a spinning coin. While it's in the air, it's not just heads or tails, it's both. A qubit is like that, only much more precise and mathematical. It's described by a wave function which assigns probabilities to being measured as 0 or 1. But until it's measured, it exists in a combination of both. This means that 2 qubits can represent 4 possible states at once. 0, 0, 1, 1, 0, and 1, 1. 3 qubits, 8 states. 4 qubits, 16, 5 qubits, 32. Each additional qubit doubles the number of simultaneous states the system can explore. With just 20 qubits, you could represent over 1 million states at once. With 50 qubits, over 1 quadrillion, that's 1 followed by 15 zeros. This exponential scaling is where quantum computers get their potential power. It's not just about speed, it's about parallelism. A quantum computer can process an astronomical number of possibilities all at once using a single set of C-kits rather than checking each possibility one at a time as a classical computer would. Now, it's important to say that quantum computers don't replace classical ones. They're not better at everything. They're better at specific types of problems. Problems involving optimization, factoring large numbers, simulating quantum systems, and more problems that involve many variables and many possible paths. Think of it this way. A classical computer is like a very fast, very diligent librarian who can search every book in a library one by one. A quantum computer is more like a magical librarian who opens all the books at once, reads them all in parallel, and then gently collapses the answers into a meaningful result. But this magic comes with a catch. Quantum systems are delicate. Qubits are easily disturbed by heat, light, or stray electromagnetic fields. Even the tiniest amount of environmental noise can destroy the fragile quantum states that make computation possible. This problem is known as decoherence, and it's one of the biggest challenges in building practical quantum computers. To keep qubits coherent, they need to be isolated in ultra-cold environments, sometimes just a fraction of a degree above absolute zero. That's 273, or in other words, very chilly. Different quantum computing platforms use different physical systems for qubits. Some use trapped ions, individual atoms held in place by electric fields. Others use superconducting circuits, tiny loops of metal that allow electrons to move without resistance. Some even explore photons of light using their quantum states to encode information. Each method has its pros and cons. There's no universal agreement yet on the best way to build a quantum computer. It's a bit like the early days of classical computing when people were experimenting with punch cards, vacuum tubes, and magnetic tapes. The field is young, experimental, and full of promise. One of the most famous quantum algorithms is Shor's algorithm, developed by mathematician Peter Shor in the 1990s. It shows that a quantum computer could factor large numbers exponentially faster than any known classical algorithm. This has huge implications for cryptography, because many modern encryption systems rely on the difficulty of factoring large numbers. If a powerful enough quantum computer were built, it could potentially break widely used security protocols. But don't worry just yet. Quantum computers are still in their infancy, and quantum-resistant encryption methods are already being developed. Another important quantum algorithm is Grover's algorithm, which speeds up search problems. While it doesn't provide exponential speed-up like Shor's, it still offers a significant improvement over classical methods. But beyond algorithms, one of the most exciting applications of quantum computing is in simulating quantum systems themselves. Ironically, quantum mechanics is extremely hard to simulate using classical computers. The number of variables involved grows so rapidly that even powerful supercomputers struggle. But a quantum computer by its very nature behaves according to the same quantum rules. It's like using water to simulate waves. The match is perfect. This means quantum computers could help us better understand chemical reactions, material science, and even drug discovery. They could allow researchers to model how molecules interact with incredible precision, leading to new medicines, better batteries, and breakthroughs in energy production. Now, let's be clear. Quantum computing isn't a miracle switch. It's not about solving every problem faster. Some problems don't benefit from quantum acceleration at all. But for the problems it can help with, the potential is enormous. And despite its complexity, there's something strangely beautiful about quantum computing. It's a union of logic and uncertainty, of probability and precision. It takes something abstract, the wave function, and turns it into a tool for discovery. It's also a reminder of how far we've come. Only a few decades ago, the idea of building a machine based on superposition and entanglement would have seemed like science fiction. Now, companies and research labs around the world are building prototypes. Quantum processors with dozens of qubits already exist. Researchers are testing quantum networks. Some quantum computers can even be accessed online. We're still in the early days, more bicycle than rocket ship. But the road is being paved, and like all quantum phenomena, quantum computing challenges our intuition. It asks us to think in terms of possibilities instead of certainties. It reminds us that the world is richer and stranger than it seems. Just imagine a computer that doesn't just answer a question, but explores all possible answers at once. A device where logic and uncertainty are partners, where memory exists not as zeros and ones, but as shimmering clouds of maybe. So the next time you use your laptop, or check your phone, or ask a voice assistant what the weather will be, think of the quantum future of machines that think in probability of information, not as a string of facts, but as a living waveform and of tiny chilly circuits, humming quietly, holding the power of maybe in their grasp. And who knows, someday, perhaps not too far from now, the most powerful ideas in the universe might be running silently on quantum machines. Thinking, simulating, dreaming in a language written not in black and white, but in the soft and subtle shades of quantum grey. Let's take a moment to relax and imagine that we're peering into the heart of a mystery. Not a detective mystery with a pipe-smoking sleuth, but a mystery of existence, of how the universe works beneath its surface when no one is looking. We've talked about superposition, entanglement, uncertainty, and the ghostly collapse of wave functions. But now comes a natural and rather unsettling question. What does it all mean? This chapter is about the interpretations of quantum mechanics, different ways of understanding what quantum theory is really telling us about reality. Because as astonishingly successful as the mathematics of quantum physics has been, predicting results, building technology, and shaping modern science, it still leaves us with a lingering philosophical itch. We know how to do the calculations, but we're still not entirely sure what those calculations describe. What is a wave function? Does the universe actually split? Is there a preferred reality? Or is reality fundamentally unknowable until we interact with it? Let's drift gently through some of the most well-known interpretations. Not too fast, no sudden movements, just a calm stroll through the garden of quantum thought. We begin with the Copenhagen interpretation, one of the oldest and most widely taught versions of quantum theory developed in the 1920s by Niels Bohr and his colleagues. It offers a kind of minimalist philosophy. The wave function is just a tool for predicting outcomes, nothing more. In this view, quantum systems don't have definite properties until they're measured. An electron isn't here or there. It's described by a wave function, a spread of probabilities. Only when we measure it does the wave function collapse into a single result or emphasize complementarity. The idea that particles can behave like waves and like particles depending on how we measure them. The measurement defines the context. Reality doesn't exist in a fixed way until it interacts with something. Copenhagen is practical, clean, and in some ways unsatisfying. It says, don't ask what's really going on. The theory works. Be content with the answers it gives you. It's a bit like someone handing you a magic coin that always lands exactly how you need it to, but refusing to explain how the coin works. This interpretation was the dominant view for many decades, and for many physicists, it still is. But some minds have never been content to stop at don't ask. Let's float now into one of the most striking and imaginative possibilities, the many worlds interpretation. This idea was proposed by Hugh Everett Bether in the 1950s, and it removes one of the most uncomfortable parts of the Copenhagen interpretation, the collapse of the wave function. In many worlds, the wave function never collapses. Instead, every possible outcome of a quantum event actually happens. All the possibilities exist, just not all in the same universe. When you measure a quantum system, say the spin of an electron, you might see spin up, but somewhere else in a parallel branch of reality, another version of you sees spin down. The universe splits, branching into two, with each possible outcome realized. This happens not just for electrons, but for every quantum event. The universe is constantly branching endlessly into a sprawling multiverse of alternate realities. In this view, superposition isn't a sign of indecision. It's a real physical state that evolves deterministically. The randomness we observe is just the result of living in one particular branch of a much larger cosmic tree. Many worlds is elegant in its mathematics. It uses only the standard rules of quantum mechanics. No wave function collapse, no hidden variables. It treats the wave function as completely real. Everything is described by the mathematics of a single evolving quantum state. But there's a catch. It's hard, maybe impossible to test, and it leads to some mind-bending consequences. If many worlds is true, then there are countless versions of you branching off at every moment. In one universe, you had tea instead of coffee this morning. In another, you never read this sentence. In another, the cat learned to talk and started a podcast. It's a compelling idea, but also deeply strange. Still, many physicists and philosophers take it seriously. Now, let's shift to something a little more classical in flavor. The pilot wave theory, also known as Bombian mechanics, named after physicist David Bohm. In this interpretation, particles always have definite positions and velocities. They're not just clouds of probability. They're real physical things moving along specific paths. So, what about the wave function? It's still there, but it doesn't represent probabilities. Instead, it acts like a kind of pilot wave that guides the motion of particles. Think of it like a surfer riding a wave. The particle is the surfer. The wave function is the ocean's swell that determines where the surfer goes. This theory is deterministic. There's no randomness. If you knew all the starting conditions, you could in principle predict everything. The trick is that the pilot wave evolves according to the standard shrouding equation, and it influences the particle's motion without being influenced in return. The weird quantum effects like interference and tunneling emerge naturally from this guiding wave. Pilot wave theory restores a kind of realism to physics. It says particles are always somewhere, always something. But it introduces a new problem, non-locality. Because the guiding wave exists in a higher dimensional space, particles can instantly affect one another, even at a distance. That's uncomfortable for those who prefer theories grounded in local cause and effect. Still, Bohmian mechanics is mathematically consistent, reproduces all the standard results of quantum theory, and offers a deterministic alternative to the fuzzy indeterminism of Copenhagen. Now, let's gently wander into another set of ideas, objective collapse theories. These say, yes, wave functions collapse, but not because of measurement or observation. Collapse is a real physical process. In these theories, wave functions spontaneously collapse over time, especially when the system gets large enough or complex enough. In other words, the universe itself decides when things become definite. Observation isn't required. One well-known version is the GRW theory named after Girardi and Weber. It introduces occasional random collapses into the evolution of the wave function. Most of the time, quantum systems behave normally, but every so often, boom, collapse happens. The larger the system, the more frequent the collapse. This kind of theory has the advantage of explaining why we don't see superpositions of cats or tables or people. It builds collapse into the theory itself without needing consciousness or measurement. But it also introduces new elements that are not part of standard quantum mechanics, and these collapses are very difficult to detect experimentally. Still, some physicists believe objective collapse is the key to resolving the measurement problem. For those who enjoy a philosophical twist, there's cubism, short for quantum Bayesianism. In this view, the wave function isn't a description of an objective physical system. It's a reflection of our knowledge, or rather our beliefs about the system. It's personal, subjective. According to cubism, quantum probabilities are not out there in the world. They live inside us as agents making bets about the outcomes of future experiences. When a measurement happens, it doesn't collapse the wave function. It updates our beliefs. Just like a poker player adjusting their odds after seeing a new card, this interpretation shifts the focus away from objective reality and toward experience. It's less about what the world is and more about how we interact with it. Cubism is elegant, modern, and rooted in Bayesian probability theory. But it also sidesteps the question of what the wave function actually is. It's useful. But is it real? Well, that depends on how you define real. So, where does this leave us? We've explored many possible ways to interpret the strange world of quantum mechanics. None of them are proven. All of them are consistent with the known experiments. Each one offers a different lens through which to view the same mysterious math. Some physicists pick a favorite. Others prefer to work without interpretation, just doing the math and letting the philosophical questions drift by like clouds. And you get to decide which version resonates most with you. Do you like the clean pragmatism of Copenhagen, the poetic branching of many worlds, the quiet determinism of pilot wave theory, the spontaneous clarity of objective collapse, or the personal subjectivity of cubism? Maybe you don't need to choose at all. Maybe like a quantum system, your understanding can exist in superposition, embracing many possibilities all at once without needing to collapse into a single belief. After all, uncertainty is not just a principle. It's also an invitation to wonder, to explore, to dwell comfortably in the space between answers. So, as you close your eyes, if you haven't already, let your thoughts drift like wave functions, uncollapsed, undisturbed, and full of possibility. And remember, no matter how strange the universe becomes, you're a part of it. You too are made of probabilities and patterns, a conscious observer in a world that might be dreaming right along with you. Let us now take a gentle detour away from photons and particles smashing in sterile labs and into the heart of something far more familiar. Life itself. Plants stretching toward the sun. Birds migrating across continents. Your own body thinking, breathing, dreaming, made up of billions of molecules dancing in harmony. All biological processes, all life. But could it be, just possibly, that life itself relies on quantum physics? It's a curious thought. For much of modern history, biology and quantum mechanics have lived in separate neighborhoods. Biology, the study of the squishy, the warm, the wet. Quantum physics, the realm of the cold, the isolated, the unfathomably tiny. One is messy, the other mathematical. One deals in blood cells and beehives, the other in electrons and probability clouds. And yet, over the past few decades, a new field has begun to blossom in the space where these worlds overlap. It's called quantum biology. And while it's still young and full of open questions, it's offering us tantalizing glimpses into how quantum phenomena may shape the very foundations of life. Let's begin our quiet journey with something green. Photosynthesis is one of the most important processes on Earth. It's how plants, algae, and certain bacteria convert sunlight into chemical energy. Every leaf, every blade of grass, every towering redwood is a solar panel powered by photons. But here's the curious part. When a photon from sunlight hits a leaf, its energy must be transferred from one part of the photosynthetic system to another. Specifically, from antenna pigments to something called the reaction center. Where the real chemistry happens is a bit like dropping a marble onto a pinball machine and hoping it lands in just the right place. You'd think this transfer might be a random walk, energy bouncing around from molecule to molecule until eventually maybe it hits the jackpot. But experimental evidence suggests otherwise. In some systems, this energy moves with astonishing efficiency, far better than a simple bounce and wait approach would allow. So how enter quantum coherence? Some researchers believe that during this energy transfer, the excine, the packet of energy created by the photon, doesn't just choose one path. Instead, it explores multiple paths at once in a quantum superposition and finds the most efficient route to the reaction center. It's as if the marble doesn't roll around. It splits, explores every possible pinball path simultaneously, and then collapses into the shortest one. Experiments using ultra-fast lasers and sophisticated spectroscopy techniques have detected evidence of quantum coherence lasting for surprisingly long times in these systems, even in the warm, wet environment of living cells. That's unexpected. We usually think quantum effects are easily destroyed by heat and noise. And yet here they are quietly helping leaves turn sunlight into sugar. It's a subtle, almost poetic idea that every tree, every flower, every green thing might be using quantum mechanics to thrive. Now, let's take to the skies. Every year, migratory birds like the European robin travel thousands of kilometers navigating with breathtaking accuracy. They don't carry maps. They don't have GPS. And yet, somehow they seem to know exactly where they're going. One theory is that they can see Earth's magnetic field. This might sound like science fiction, but evidence suggests that some birds possess a kind of quantum compass in their eyes based on molecules called cryptochromes. Here's how it might work. When light hits the cryptochrome molecule, it excites an electron, creating a radical pair. Two electrons on separate molecules, each with a spin, and the two are quantum entangled. The magnetic field of the Earth subtly influences how these spins evolve. Depending on the orientation of the bird's head and body, the magnetic field shifts the balance between singlet and triplet states in the radical pair, altering the chemical outcome of the reaction. In simple terms, the quantum state of these electrons changes depending on the direction of Earth's magnetic field. And that change can trigger a different chemical signal in the bird's retina. The bird might literally see a pattern, a dark or light spot that helps it orient itself geographically. It's still being studied, but experiments have shown that disrupting these quantum states with certain kinds of light or magnetic fields interferes with the bird's ability to navigate. If true, then deep inside the eye of a robot, quantum entanglement may be quietly guiding it across oceans and continents. Nature, it seems, has been using quantum tools long before we gave them names. Now, let's return home to the humble human nose. The traditional theory of smell is all about shape. Molecules drift into your nose, bind with receptors that fit them like a key in a lock, and voila, you smell roses or coffee or freshly baked bread. But there's a problem with this theory. Some molecules that are nearly identical in shape smell completely different, and some that are very different in shape smell exactly the same. This led some scientists to suggest that smell might not just be about shape. It might also involve vibration, and that quantum tunneling might play a role. In this vibrational theory of elaction, when a molecule binds to a receptor, it doesn't just sit there, it vibrates. And if that vibration matches a specific frequency, it can enable quantum tunneling of electrons between parts of the receptor, triggering a signal to the brain. It's like striking the right note on a tuning fork. Only when the molecule vibrates, just so does the electron leap through the quantum barrier and send the message, "This is vanilla." This theory is still controversial and far from proven, but it's a reminder that even something as ordinary as sniffing a flower might involve subtle quantum processes. So far, we've wandered through forests, flown with birds, and followed our noses. But what about you? Your brain, your body, your thoughts? Could quantum effects be playing a role inside your neurons is a delicate question. The brain is warm, wet, and noisy, a place where quantum coherence shouldn't survive for long. But some researchers believe there may be microstructures inside neurons called microtubula that could support quantum processes. This idea, part of the Orco theory proposed by Roger Penrose and Stuart Hamath, suggests that quantum effects inside microtubules may be linked to consciousness itself. Now, this is highly speculative. The idea is not widely accepted in the neuroscience community, but it's part of a growing curiosity about whether quantum mechanics might help explain phenomena that classical biology still struggles with. Whether or not consciousness is quantum, the idea invites us to look at the brain not just as a collection of wires and chemicals, but as something deeply interwoven with the laws of physics at every level. And isn't it beautiful to think that your thoughts, drifting gently towards sleep, might be supported by processes reaching all the way down to the quantum scale? Quantum biology is still in its early days. Many of its claims are still debated. But even the possibility that life relies on quantum phenomena opens up a world of wonder. It reminds us that biology is not separate from physics, that evolution in its tireless tinkering may have discovered and refined ways to harness quantum weirdness long before we did. That inside every leaf, every eye, every breath, there may be a hidden quantum heartbeat. So, as you lie still, consider this. The atoms in your body are ancient, born in stars shaped by chemistry, and now arranged in a way that allows you to wonder, to feel, to be. And maybe, just maybe, part of that being is built not just from molecules and muscles, but from the shimmering, dancing rules of quantum mechanics. The rules that let particles tunnel through walls, that let electrons be here and there, that let birds find their way home by looking at the sky and seeing invisible forces. In the end, quantum biology invites us to soften the borders between disciplines and between ourselves and the world, to see not a division between science and life, but a tapestry woven together atom by atom, wave function by wave function, dream by dream. Let's take a deep, quiet breath together as we prepare to look not just down into the quantum world, but outward toward the grand star-speckled universe. So far, we've explored how quantum mechanics governs the very small particles, atoms, light, and the occasional cat-in-a-box paradox. But quantum mechanics doesn't stop at the microscopic. In fact, it's the foundation upon which everything stands, including galaxies, including you. In this chapter, we'll explore how the strange, delicate rules of the quantum realm ripple outward into the everyday world, how they shape the chemistry of your body, the structure of stars, and the very birth of the universe itself. Because even though quantum physics seems abstract and far removed from daily life, it's quietly at work behind the scenes, scripting reality in soft subatomic strokes. Let's begin with something very close to home: atoms. Atoms are tiny, of course, but within those tiny packages lies an entire blueprint of quantum behavior. The very structure of atoms, the way they hold together, is governed by quantum rules. Take the electron, a ghostly, jittery little particle that orbits the nucleus. In classical physics, we might imagine electrons moving around the nucleus like planets around the sun. But in quantum physics, electrons don't follow neat, predictable paths. Instead, they exist in orbitals, regions of probability, fuzzy clouds where they're likely to be found. These orbitals have shapes, spheres, dumbbells, and other more exotic forms. Not because electrons are decorating their space, but because of quantum wave equations. The behavior of the electron is governed by the Schrödinger equation, and its solutions tell us where the electron is most likely to be. And here's something beautiful. Only certain energy levels are allowed. Electrons can't just take up any space they like. They must snap into place at specific energy states. This is what gives atoms their structure. It's why hydrogen behaves differently from helium, why oxygen bonds so easily, why gold glows yellow and copper shines red. Every molecule in your body, every strand of DNA, every protein, every breath is made possible by electrons obeying the strange rule-bound world of quantum mechanics. Without quantum theory, chemistry simply wouldn't exist. Now, let's float a little deeper into the structure of atoms. One of the most important quantum rules is called the Pauli exclusion principle, discovered by Wolfgang Pauli in the early 1920s. It says that no two fermions particles like electrons can occupy the same quantum state at the same time. Imagine trying to seat guests at a dinner party where no one is allowed to sit in the same chair. Even if there are an infinite number of identical chairs, the electrons must spread out. They must each find their own state. This rule is why atoms don't collapse. It's why electrons don't all pile into the lowest energy level and sit on the nucleus like sleepy puppies on a warm lap. Instead, they're forced to build up into structured shells, each electron finding its own unique configuration. The Pauli exclusion principle is also the reason why matter takes up space, why you can't walk through walls, why your hand doesn't sink into the table, the resistance you feel when you push on a solid object. That's the effect of countless electrons refusing to share quantum states. It's an invisible universal, no thank you from the building blocks of matter. Now let's move from atoms to molecules and from structure to behavior. Molecules form when atoms bond together, and bonding is an entirely quantum phenomenon. There are several types of chemical bonds: covalent, ionic, hydrogen, but at their core, they all rely on electrons being shared, attracted, or exchanged between atoms. The key to all of it lies in quantum mechanics. Electrons aren't just glued between atoms like mortar between bricks. They form molecular orbitals, which are combinations of atomic orbitals. These molecular orbitals can be bonding or antibonding, stable or unstable, and their shapes and energies determine whether a molecule holds together or falls apart. Quantum mechanics predicts the angles of chemical bonds, the shapes of molecules, and even the colors they absorb and reflect. That's how we know what makes leaves green, what gives blood its red hue, and why bees can see ultraviolet. It's how your brain releases neurotransmitters, how enzymes speed up reactions, how cells convert glucose into energy. The entire machinery of biology is driven by chemistry, and chemistry is governed by quantum rules. Without quantum mechanics, there would be no water, no DNA, no coffee, no cookies, just a soup of unstructured particles politely refusing to connect. Let's look up now into the night sky. The light you see from stars, those distant points of fire, is born from fusion, a process governed by quantum mechanics. Deep in the cores of stars, hydrogen atoms are smashed together under immense pressure and temperature. But even then, they don't have quite enough energy to overcome the electrostatic repulsion of their positively charged nuclei. So, how do they fuse? They tunnel. Quantum tunneling allows protons to bypass the classical energy barrier. It's as if the particles decide, well, I can't go over the mountain, but maybe I can sneak through it. Fusion wouldn't happen without this little quantum shortcut. The sun would not shine. Life on Earth would not exist. The very process that powers the stars depends on a quantum effect that seems impossible in the classical world. And what happens when stars die? Some become white dwarfs, dense corpses of stellar matter held up not by heat, but by something called electron degeneracy pressure. That's just a fancy name for the Pauli exclusion principle in action again. Electrons don't want to share the same quantum state, so they push back, preventing the star from collapsing further. heavier stars collapse even more, becoming neutron stars, where not just electrons but protons and neutrons are squeezed together under similar quantum pressures. And in the most extreme cases, black holes, even quantum theory begins to strain. Gravity becomes so strong that not even light can escape. And we still don't fully understand what happens at the quantum level inside those dark regions. But many physicists believe that a full theory of quantum gravity, the unification of general relativity and quantum mechanics, may one day unlock the secrets of black holes and the fabric of spacetime itself. Let's zoom back now, way back to the beginning. The early universe, moments after the Big Bang, was a quantum playground. Space and time were fluctuating wildly. Matter and energy existed in a kind of foamy blur governed by probabilities and uncertainty. In fact, many cosmologists believe that quantum fluctuations in the early universe gave rise to the large-scale structure we see today. Tiny differences in density caused by quantum randomness were stretched out by inflation and eventually became galaxies, stars, planets, and people. In this view, everything can be traced back to a quantum jitter. You lying there listening to this are the result of ancient fluctuations in a vacuum magnified by the expansion of space. Your atoms were born in stars. Your breath shaped by chemistry. Your thoughts guided by neurons firing in patterns sculpted by quantum rules. The universe is quantum all the way up. It's easy to think of quantum mechanics as confined to the microscopic. But in truth, the distinction between the quantum and the classical is more of a gradient than a wall. The classical world, the world we see and touch, is not separate from quantum mechanics. It emerges from it. The behavior of large objects arises from the collective behavior of quantum particles, smoothed out by statistics and noise. A table is stable because its atoms are stable. Its atoms are stable because their electrons are in quantized energy states. And those energy states exist because of the wave-like nature of particles. The solidity of the world is built on the uncertainty of its parts. It's humbling, isn't it? The things that feel most real, your heartbeat, your coffee mug, the floor beneath your feet, are grounded in phenomena you'll never see. Invisible patterns, subatomic probabilities, tiny dancing wave functions adding up to something solid. Quantum mechanics may seem strange, but it's not separate from life. It is life. It's the framework behind the scenes, the artist behind the canvas, the quiet whisper beneath every loud reality. So as you drift into rest, let your mind relax into that idea that you are part of a quantum universe. Not in metaphor, but in fact that your every cell, every thought, every moment is built on particles that behave not like marbles, but like melodies uncertain, interconnected, and deeply beautiful. The large is made of the small, the certain is built from uncertainty. And even here in the stillness of your room, the quantum world is humming softly, guiding the stars, holding your breath, and perhaps gently rocking you to sleep. Let's take a calm, cleansing breath and shift gently now from the grand to the grounded. We've explored electrons dancing through barriers, birds possibly navigating by quantum compass, and the universe itself unfolding from quantum whispers. But with all this wonder, all this mystery comes a curious shadow, the myths. Quantum physics, for all its beauty and elegance, has also become a magnet for misunderstanding. Perhaps it's because it's so counterintuitive, or perhaps it's because it wears the cloak of mystery so convincingly. Whatever the reason, quantum mechanics has gathered around it a swirling fog of myths, half-truths, and misunderstandings. So, let us now very gently take a lantern in hand and stroll through the fog, clearing the air with kindness and curiosity. Because understanding what quantum physics isn't can be just as soothing as knowing what it is. Myth 1. Quantum physics says you can change reality with your mind. This is perhaps the most persistent quantum myth of all. You may have heard it before, phrased like a cosmic secret. Your thoughts shape reality, or quantum physics proves that by focusing your intention, you can change the world around you. It sounds empowering, it sounds poetic, and in some ways, it's understandable why this idea is so attractive. If the observer affects the system and we are observers, then surely our thoughts must be powerful agents of change, right? Well, not quite. Yes, quantum mechanics tells us that observation plays a role in determining the outcomes of measurements. But in physics, observation means measurement, an interaction between a quantum system and a measuring device. This doesn't require human consciousness. A geocounter, a photon detector, or even a stray particle in the environment can cause wave function collapse. Your thoughts, however lovely, are not collapsing wave functions across the cosmos. The quantum system doesn't need to know you're watching. It just needs to be disturbed by something, anything that forces it to commit to a specific state. In short, you're wonderfully complex and your thoughts matter deeply in your life. But they do not control the trajectory of electrons or make particles jump through quantum hoops. Reality is not your personal projection screen. It's a shared canvas. And quantum physics is part of the paint. Myth 2. Quantum entanglement means faster than light communication. Here's another idea that has sparked countless headlines and sci-fi daydreams. Quantum entanglement lets you send messages instantly across space, as if two people separated by galaxies could whisper secrets to each other via spooky quantum action. Let's pause and clarify. Quantum entanglement is very real, and it is deeply strange. Two particles can become linked in such a way that measuring one instantly determines the state of the other regardless of the distance between them. That part is true. But what's not true is that this can be used to send information faster than light. Here's why. When you measure your half of an entangled pair, the result is random. You can't control what you get. You just get spin up or spin down, for instance. The other person far away measures their particle and also gets a random result. Only later, when you compare your measurements using classical communication subject to the speed of light, do you notice the perfect correlation. So, while entanglement creates a kind of instantaneous connection, it does not allow for instant messaging. No signal travels faster than light. No data is transmitted. There is no quantum walkie-talkie. It's strange. It's mysterious, but it's still consistent with Einstein's speed limit. Myth 3. Schrodinger's cat is both dead and alive. Yes, the poor cat. This is the metaphor that launched 1,000 jokes and perhaps just as many misunderstandings. Irving Schrödinger's cat, you may recall, is a thought experiment meant to highlight the absurdity of applying quantum principles to everyday objects. In it, a cat is sealed in a box with a radioactive atom, a poison vial, and a trigger mechanism. If the atom decays, the vial breaks and the cat dies. If not, the cat lives. But quantum physics says the atom exists in a superposition, decayed and not decayed until observed. So the cat too must be in a superposition, dead and alive. Now some people take this literally. They imagine that the cat is actually both dead and alive, frozen in a ghostly in-between state until someone opens the box. But that's not the point of the thought experiment. Schrödinger wasn't saying that cats exist in dual states. He was pointing out the weirdness, the discomfort of extending quantum principles to large macroscopic objects. In reality, decoherence prevents things like cats from entering superpositions in the way that electrons do. The cat is constantly interacting with its environment, air molecules, photons, vibrations. These interactions collapse any potential superpositions long before a human ever peeks inside. So no, there is no limbo cat haunting the inside of a box. The thought experiment is a philosophical prompt, not a prediction of zombie felines. Myth 4. Quantum physics is just random and chaotic. It's easy to hear about wave function collapse and probabilistic outcomes and assume that quantum physics is just a cosmic coin toss, that it's all chance, no order, that anything can happen at any time. But this too is a myth. Quantum physics is deeply structured. It is governed by precise mathematical rules, elegant equations that predict with astounding accuracy the behavior of particles and fields. Yes, individual outcomes may be probabilistic. You can't say exactly where an electron will land, but you can say with extreme confidence how likely it is to land in any given spot. This makes quantum mechanics not chaotic, but statistical. It's more like weather than roulette. We can't predict the exact temperature of a breeze at 300 in the afternoon next Thursday, but we can model the system and understand the patterns it follows. Randomness exists, but it's cradled in order. Myth 5. Quantum physics means anything is possible. This one is often used to justify all sorts of things. Telepathy, teleportation, mind over matter. If the quantum world allows particles to be in two places at once or to pop through barriers, then surely anything must be possible. Well, not quite. quantum physics does allow for strange things, but it also sets strict boundaries around what's possible. There are rules, mathematical, observable, testable rules. You can't break the conservation of energy just because it feels good. You can't make an electron travel faster than light by wishing on a star. Quantum physics expands our understanding of what nature can do, but it does not throw out logic, consistency, or evidence. In fact, quantum theory is one of the most experimentally confirmed theories in all of science. So, while the quantum world is strange, it's not a blank check for magical thinking. Now, if you've ever believed or repeated any of these myths, don't worry. They're popular for a reason. They speak to a desire to feel connected to the deeper workings of the universe. And there's something beautiful in that impulse. But understanding the true nature of quantum mechanics is even more magical because it tells us that the world is strange, beautiful, and deeply connected. Not because we want it to be, but because that's how it is. Quantum physics doesn't say that your thoughts create reality, but it does say that measurement shapes outcomes. It doesn't give us faster-than-light messaging, but it does suggest that particles, once linked, remain connected in a way we're still learning to understand. It doesn't say that a cat is both dead and alive, but it does say that the world isn't always what it seems until we interact with it. And perhaps that's the softest and most powerful truth of all. That reality is participatory, that it's shaped by relationships, that even the smallest piece of the universe responds to its context. So, as you lie there relaxing, drifting, perhaps even smiling softly at how strange things can be, let this be your takeaway. The real quantum world is more interesting, more subtle, and more full of wonder than any myth could ever make. Not because it bends to our will, but because it whispers secrets, truth stranger than fiction, just waiting for us to listen. And now, as we float gently to the end of this quiet journey through the strange world of quantum physics, let's return softly, curiously, to where we began. We started with a simple invitation to relax, to wonder, and to drift through a universe that is far more mysterious, elegant, and peculiar than it first appears. A universe where particles can be in many places at once, where actions ripple across vast distances without crossing them, where the act of observing shapes the very thing being observed. A universe built not on certainties but on possibilities. We've met electrons that dance like waves. We've watched photons slip through two slits at once. We followed entangled particles and tiptoed through the philosophical fog of quantum interpretations. We've seen tunneling particles spark stars into life, and we've wandered through a forest where plants might quietly use quantum coherence to drink in the light. And through it all, one thing has remained clear. The more we learn, the more astonishing the world becomes. Not because it always gives us the answers we expect, but because it dares to behave in ways we never would have imagined. So, let me ask again, just as I did at the beginning, where in the world are you listening from? What time is it in your quiet little corner of the cosmos? And if you're still awake, have you made it this far because you're still wide-eyed with curiosity, or just wonderfully sleepy? If this strange and beautiful journey through quantum physics has helped you wind down, helped you relax, or simply filled your evening with a gentle sense of awe, I would be so grateful if you'd give this video a like, and perhaps even subscribe for more calm adventures through science and wonder. Thank you truly for being here. Now, whether your night leads to dreams of wave functions and starlight, or you've already drifted into the soft silence of sleep, remember this. The universe is not made of things. It is made of stories, of patterns, of probabilities. And you, dear listener, are part of that unfolding story woven quietly, exquisitely into the fabric of reality itself. Sleep well, and I'll see you again next time.